Hi everyone, welcome back. I'm Devasatham and you're watching the fifth lecture of EE635 Applied Linear Algebra, the fourth and final module. Okay, so far we have seen various important things about vector spaces, namely uh, linear independence, yeah, the concept of linear independence. With that concept immediately followed the idea of basis. Let me remind you that a basis is nothing but a generating set that is also linearly independent, right? And then we saw some really remarkable results about this basis. We found out that if there is a vector space which is generated by m number of elements, m number of vectors, then any collection that is uh, any collection of vectors more than m can never be linearly independent. They have to be necessarily linearly dependent. And that from there it followed that if there is a finite dimension, if there is a vector space which admits a finite basis, then every other basis will have exactly the same number of elements in it. And that invariant is called the dimension of that vector space. Right? In this scenario, we call this a finite dimensional vector space. When it turns out that the basis, there is no finite basis of a vector space, then we call it an infinite dimensional vector space. And then we saw some consequences of this idea about basis, right? In this module, what we're going to see is one more immensely interesting uh, consequence of this idea of a basis for the case of finite dimensional vector spaces, right? This idea is, the name of this idea, the formal name of this idea is coordinates. I'm sure you have heard this term before in coordinate geometry. So if I remember correctly, what we learn in high school about coordinates is that in this, let's say 3D Euclidean vector space, I have x1, x, y, z, three axes. Then a point is specified by its component along x, along y, along z. These three components individually are called the coordinates. So x coordinate, y coordinate, z coordinate. You may also have heard of this coordinate terms, this term coordinate in connection with, say, geography or anything that has anything to do with the earth. So coordinate of a particular space, a particular place. Like for example, what is the coordinate of Mumbai? Yeah, you say lat long, right? Here we'll see how this idea of just lat long or x, y, z coordinates can actually be extended to any arbitrary finite dimensional vector space. Yeah, and how it helps us in solving various different problems coming from electrical engineering and other branches of engineering. Yeah, let me try and share my screen here. I hope it should be up any point. Right. Okay, I hope I'm also visible. Okay, so let's start with this idea of a coordinate. Now, what we first need to notice is the following. So suppose V is a, so like always, we are going to treat things in an abstract manner. So we start with an abstract vector space V. So let V be a vector space over a field F. Let us also assume that, suppose dimension of V, say n, is finite. So it's a finite dimensional vector space. Okay. Now, for this finite dimensional vector space, say B, which is V1, V2, dot 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 Vn, is a basis. Okay. So then that means for any arbitrary v, in the vector space, there exists alpha 1 dot 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 up to alpha n from the field such that v is equal to alpha 1 v1 plus dot 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 up to alpha n vn, right? So this is the expression of the arbitrary vector v as a linear combination of v1 up to vn, because v1 up to vn generates all of v, yeah, as linear combinations. It means that for any arbitrary vector v, there should be such a linear combination, right? What is interesting here is that because v1 up to vn is a basis, that is, they are linearly independent, these numbers alpha 1 up to alpha n, these scalars, they are unique for this v. That means somebody gives me a v, I write this expression is unique. For a different v, I will have a different expression, but for a given v, it's going to be unique. Why? Let us just check that. Yeah. So suppose this is not. So we claim that alpha 1 dot 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 up to alpha n is unique, right? Why? Suppose there exists alpha 1 prime dot 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 up to alpha n prime scalars such that the same v is equal to alpha 1 prime v1 plus dot 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 up to alpha n prime vn. Suppose we have another linear combination like this. What happens then? Suppose this is my equation 1, this is my equation 2. So if I subtract equation 2 from 1, what we get is v minus v on the left hand side. So it's the zero vector. That is equal to alpha 1 minus alpha 1 prime into v1 plus dot 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 up to alpha n minus alpha n prime into vn. Right? Now we come back to our idea of linear independence. So here is a linear combination of linearly independent vectors that goes to 0, right? But what we know about linearly independent vectors, the only linear combination that can go to 0 is the trivial linear combination. So this implies, since v1 up to vn is linearly independent, this implies alpha 1 minus alpha 1 prime must be 0, alpha 2 minus alpha 2 prime must be 0, all these coefficients must be 0, alpha n minus alpha n prime must be 0, which implies alpha 1 is equal to alpha 1 prime, alpha 2 is equal to alpha 2 prime, so on up to alpha n is equal to alpha n prime. So all the coefficients are in fact equal, right? They're not distinct. Alpha 1 is same as alpha 1 prime, alpha 2 is same as alpha 2 prime, and so on. So it's the unique linear combination. So therefore this expression is unique, which means to every vector v, there exists a unique n tuple alpha 1 dot 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 up to alpha n such that v is equal to alpha 1 v1 plus dot 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 up to alpha n vn. This is the first observation. Remember this. We'll come back to this very soon. Before we come back, let us observe two more very interesting facts about this thing. What is that? Suppose W is another arbitrary vector in V such that W is equal to beta 1 V1 plus dot 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 up to beta n Vn, right? Isn't because for every vector there is a unique linear combination. Suppose W is another vector, so I'll have one more linear combination like this. Notice that if I do V plus W, that is vector addition of two vectors, what do I get? I get alpha 1 V1 dot 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 up to alpha n Vn and here I have beta 1 v1 plus dot 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 up to beta n vn, right? Now, of course, by all the axioms of vector addition in an arbitrary vector space, there is associativity, commutativity, distributivity, all those properties. If I apply them together, I get this expression to be equal to alpha 1 beta 1 v1 plus dot 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 up to alpha n plus b plus beta n vn. You see, the interesting part is that I had a v to which we had these linear combinations. I had w to which I had these coefficients. V plus w must be another vector. For that, I have these coefficients, and because they're unique, that's the, the coefficient that can be attached with v plus w are these coefficients, in fact, uniquely, right? Similarly, one can do for scalar multiplication. So if I have, say, alpha times v, that will certainly be alpha times alpha 1 into v1 plus dot 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 up to alpha times alpha n into v1. All these things suggest that for a finite dimensional abstract vector space, listen carefully, for a finite dimensional abstract vector space over a field F, once we fix a basis, then every vector gets uniquely associated with an n tuple, right? Those n tuples will be called its coordinates. And not just that, not just some arbitrary n tuple. These n tuples are such that the rules that we are following to get these n tuples, yeah, under that rule, adding two vectors in the abstract vector space just amounts to adding those n tuples like you would have added two n tuples. Scalar multiplication in the abstract vector space would amount to doing scalar multiplication to an n tuple. The only catch here, the only thing to remember here is that to get that n tuple, we must fix the order of v1 up to vn, right? When I say something is a basis, so when I say something is a basis, I just have to say that it's a set, right? It's a set v1 up to vn. It doesn't matter in which order I'm taking. But when I'm writing an expression, say v is equal to alpha 1 v1 plus dot 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 up to alpha n vn, there the order matters, because here I'm going to write this thing as the n tuple as alpha 1 alpha 2 dot 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 up to alpha n. This n tuple is only only unambiguous, only unambiguous when we know the order of v1 dot 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 up to vn. That is, so think of a basis, say v1 and v2, yeah, and under that basis, suppose a vector, suppose v is written as alpha 1 v1 plus alpha 2 v2. So if I take them in this order, then this will be alpha 1 alpha 2 is a so I can write this also as alpha 2 v2 plus alpha 1 v1, right? So depending upon which order I'm taking, the coefficient that I get that are different. So that's why, so we'll see this in more detail very soon. So try and understand this. So let me do it formally now. So what we're trying to say here is the following. So suppose b equal to v1 up to vn is an ordered basis. So far we have not used this term ordered basis, but that means I'm considering v1 to be the first vector, v2 to be the second vector, and so on. So I'm saying first, second, third, this order I'm putting, yeah. So in that scenario, it's called an ordered basis. So suppose we have an ordered basis. Suppose b is an ordered basis for v, which is a vector space over a field F, then there is a structure preserving one-to-one correspondence between V and F to the N. What is that? This correspondence is defined as follows. Yeah, let V in V be arbitrary. This implies there is unique alpha 1 dot 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 up to alpha n in F such that V is equal to alpha 1 B1 plus dot 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 up to alpha n Bn. Then V, the vector in V, is associated to the n tuple alpha 1 dot 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 up to alpha n. This is an element in V. Its correspondence in F to the n is this, right? This vector alpha 1, alpha 2 dot 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 up to alpha n will also be denoted by V B. This means it is a representation of V under the ordered basis B. So let me write this out. This is pronounced as representation of, this is going to be immensely important for us throughout the course. The representation of V as representation of V under the ordered basis, that is B. Yeah, I said one-to-one correspondence. That should be clear. That means that for every V, there is one and only one such representation of V under the basis, under the ordered basis B. That is one-to-one correspondence. What is structure preserving? So one-to-one, I've explained. What is structure preserving? Structure preserving means that the structure of V as a vector space over F is the same as, okay, is equivalent to the structure of F to the N as a vector space over F. That is what we have observed before, that if I have two vectors, say V and W, and representation of V under B is V, that symbol, representation of W is that symbol, then summing V plus W and then taking the representation is the same as taking representation of V first, W and then W, and then adding them. And same with scalar multiplication. So let me write, structure preserving means V, okay, let me do it this way, huh? Listen carefully. VW, V plus W's representation is V's representation plus W's representation. Note that this sum is happening over the vector space V, whereas this sum is happening over the vector space F to the N. You see? So this means, in words, this means for for a vector space, for a finite dimensional vector space with an ordered basis, the vectors in it can actually be literally treated as columns of numbers. No difference whatsoever. What we have to do is we just have to do the representation. And once the representation is done, these entries alpha 1 up to alpha n, alpha 1 will be called for a given vector, alpha 1 will be some number, right? So alpha 1 will be called the first coordinate, alpha 2 will be called the second coordinate, alpha 3 will be called the third coordinate, and so on. So these are the coordinates. Okay, right? um, so let us look at a quick example, and for that we'll go to this one. We'll go to an earlier construction that we did while we were trying to motivate, a definition of abstract vector spaces. This one, you see, I had these three vectors, w1, w2, and w, right? E to the power t plus 2 e to the power minus t, e to the power t, e to the power plus e to the power 2t, and then I have minus e to the power minus t, 2 e to the power t plus 2 plus e to the power 2t, right? So yeah, the power t, 2 e to the power minus t, e to the power t, e to the power 2t. So I have, so let me write this as these vectors. I have a vector w1 which is equal to e to the power minus t plus, sorry, I think I had e to the power t, right? Let me check one more time. Lecture 4, I have t 2 e to the power minus t, e to the power t plus 2 e to the power minus t. Then I had w2 which was e to the power t plus e to the power 2t, e to the power 2t, and then I had a vector w um, which was minus e to the power minus t, 2 e to the power t, and e to the power 2t, minus e to the power minus t plus 2 e to the power t plus e to the power 2t. I think it was the one. Yeah, that's it. So these three vectors, and I had asked the question that is w in the span of w1, w2 over real numbers. Yeah. For that, we first notice that we can look at this vector space V, which happens to be, so define V as the span over real numbers of e to the power minus t, e to the power t, and e to the power 2t. One can check actually that these three vectors are linearly independent. Check. This goes to you as a homework. Check. So immediate attention homework, that e to the power minus t, e to the power t, and e to the power 2t, this is a linearly independent set over R. Linearly independent set over R, right? So if it's a linearly independent set over R, then this can be taken as a basis, right? And this can be taken as an ordered basis. Okay, now if this is an ordered basis, then notice that how W1 comes out to be. What is W1? So let me call this as the basis B. What is W1B? What will it be? So I already have this linear combination, right? W1 is given as the linear combination e to the power t plus 2 e to the power minus t. Okay, so in the ordered basis, this is 2 multiplied e to the power minus t plus 1 multiplied e to the power t and 0 multiplied e to the power 2t. So this will be 2, 1, 0. Yeah. Similarly, tell me what W2B would be. W2, notice, is e to the power t plus e to the power 2t and 0 times e to the power minus t. So this will be 0, 1, and 1. This is going to be 0, 1, and 1, right? Now, what was the question? Is W2 a part of W1 and W2, span of W1 and W2? That question, so W is in the span of W1 comma comma W2, this question is equivalent to saying that whether there exists alpha 1 and alpha 2 real numbers such that W is equal to alpha 1 W1 plus alpha 2 W2, right? But then this is equivalent to saying W's representation in B must be equal to alpha 1 W1 plus alpha 2 W2. I didn't write about the for the structure preserving part. One more thing is, and one more thing is, which I forgot to write, alpha times V, its representation must be alpha times representation of V. This multiplication is happening in V, this multiplication is happening in F to the N. Okay, now here. So by the structure preserving part, this means this should be alpha times W1B plus alpha 2 times W2B. Okay, but what is this? WB is what? W is this one, right? So this is -1 plus 2 and plus 1. This is the same as -1 plus 2 plus 1. Whether this is a linear combination of alpha 1 times what was W1B 210 plus what is this one? This is 011. So alpha 2 times 011. So now we are back to asking the question whether such alpha 1 alpha 2 exists or not, which now notice is the same as existence of X in R2 such that 210. Remember our observation that linear combination of columns is nothing but multiplication from the right. Ax equal to b. So we are asking the question whether Ax equal to b is solvable or not. It is solvable if and only if W belongs to the span of W1, W2. Right? So this is the power of this coordinates idea. We had an abstract problem, but now we have converted that problem into an Ax equal to b problem. Yeah, I hope you will learn something from here. So try this working out. So check whether this is true or not. That you can do as a homework. Yeah, I'm not doing that here. So let us move on to another important aspect of this coordinate idea. Yeah, and what is that? So right. So once we have this coordinate, this question naturally arises that suppose I have an ordered basis, yeah, and now suppose I have another ordered basis, two different bases. So the same vector would then have two different representations. How are these representations related? Is the question clear? So question, let B1, B2 be two ordered bases for V as a vector space over F. So then, and let V in V be arbitrary. Then by the construction that we have had, we must have a V in B1 and we must also have V in B2. How are these two? What is their relation? How are they related? Yeah. This idea is known as change of basis. It is something that you have routinely done before, I'm sure. Yeah, change of variables. Long back in high school when you faced some difficult integration, you did a change of variables and it became so simple. Exactly like that. It's a change of variables. Yeah, it's a change of basis. But how this representation of a vector as coordinates how does it differ when there is a change of basis? That's the question. Okay. So for that, what we're going to do is we're going to notice first, we're going to say, okay, say B, the first order basis, suppose is given by V1 dot 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 up to Vn. This is my first ordered basis. And my second ordered basis is W1 dot 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 up to Wn. Okay, is that all right? Now, if that is the situation, because B1 is an ordered basis, every vector W1 up to Wn can be expressed as linear combinations of V1 up to Vn, right? Which means each of these W1 up to Wn can be represented as, uh, under these coordinates, which means I can, okay, so let me say that W1 is equal to, say, P11 V1 plus P21 V2 plus dot 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 up to Pn1 Vn. Similarly, W2 will be equal to P12 V1 plus P22 V2 plus dot 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 up to Pn2 Vn. That continues till I have Wn equals P1n V1 plus P2n V2 plus dot 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 up to Pnn Vn, right? Now, notice that W1 under the basis B1 is nothing but P11, P21, dot 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 up to Pn1, right? W2 P1 is nothing but P12, P22, dot 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 up to Pn2, like that. Yeah, I'm not writing it anymore, but I think you can understand. So these P entries, how many entries are there? How many such numbers are there? How many such numbers? Exactly n square such numbers. Okay. Now notice the following. So shorthand notation, Wi is equal to summation P j I v j. J goes from 1 to n. This is the notation that we have used, right? I think I didn't make a mistake here. Yeah, yeah, right. So this is the expression. Now, so suppose V is an arbitrary vector. So V is an arbitrary vector in V. Suppose V is equal to, what should I write? Beta 1 W1 plus dot dot dot. Okay, let me do it this way. This will be easier. This is alpha 1 V1 plus dot 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 up to alpha n Vn, because V1 up to Vn is a basis, and of course because W1 up to Wn is a basis, there is this expression also. Both of them are true, which actually tells us that V B1 is alpha 1 up to alpha n, and B2 is beta 1 up to beta n, like that. Yeah. Now we are going to notice this expression. We are going to play with this expression. What does that mean? Yeah. So we're going to play with this expression, this one. Yeah. So V is equal to, notice, beta 1 W1 plus dot 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 up to beta n Wn. But now beta 1, this W1 can be written by this linear combination, right? So I substitute for W1 this expression, summation P J1 Vj, j going from 1 to n, right? This is the expression for W1. Similarly, I keep on doing this and finally I get beta n. Let me write it in the new line. So it's going to be a lengthy expression. Beta n summation j going from 1 to n pj n vj. Yeah, is that all right? Okay. Now I take all the V1s together, all the V2s together, and take V1, V2, all these things out common, and I write this expression as a linear combination of V1 up to Vn from here. How do I do that? So notice what is happening to V1. What will be the coefficient of V1? The coefficient of V1. So here it will be P11 beta 1 plus in this expression it will be P12 beta 2, P12 beta 2 plus dot 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 up to P1n beta n. This entire thing will multiply to V1. Yeah, this trend will continue till I have P for Vn. I will have P in Pn. Okay, from sorry. I'll have to look at here. Here the Vn's coefficient will be P1n. Sorry, P. Here it will be Pn1 beta 1 plus Pn2 beta 2 plus dot 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 up to Pnn beta n into Vn. I think I have written the expression properly. Okay. This summation wise you can write j going from 1 to n P1j beta j into V1 plus summation j going from 1 to n P2j beta j V2 plus dot 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 plus summation j going from 1 to n Pnj beta j into Vn. That is the expression, right? Now, but this expression, we already know that V allows this expression that alpha 1 V1 plus dot 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 up to alpha n Vn. Yeah, which means this alpha 1 up to alpha n tuple. So I have two linear combinations for the same vector with same basis vector, same ordered basis, but it's unique, right? One-to-one correspondence. So which means these numbers give me one representation, coordinate representation, and alpha 1 up to alpha n gives me another coordinate representation. Because they're unique, they have to be equal. Yeah, that's it. So this means alpha 1 dot 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 up to alpha n, this n tuple is nothing but this n tuple, summation j going from 1 to n P1j beta j, so on up to summation j going from 1 to n Pnj beta j. Surprise, surprise. Not much, because this expression is nothing but P11, P12 dot 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 up to P1n, P21, P22 dot 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 up to P2n, so on like this. Finally, I have Pn1, Pn2 dot 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 up to Pnn, multiplying beta 1 up to beta n. Yeah, the cutest form of this equation is what is going to come now. Okay, the cutest form, V, the vector, its representation in basis 1, in the first ordered basis, is nothing but this matrix into V, its representation in basis 2. What are these numbers? First column is W1's representation in V1, dot 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 up to Wn's representation in V1. That's it. This matrix would be called the P matrix. Okay, right? Now, this P matrix is going to be, so this is the expression, and P of course has to be invertible. There is no way out. Why? Because you see, if this right hand side is 0, that means V is the 0 vector. Yeah, right hand side being 0 means representation of a vector under the first ordered basis is 0. So it's 0 times V1 plus 0 times V2 and so on. That's the 0 vector. Such a 0 vector, can there be a non-zero vector VB2? Can there be a non-zero n-tuple for which this is 0? No, because it's the same vector, right? It's the same 0 vector. 0 vector under any basis should give us 0 representation. The coordinates to be 0. So I know that Px is equal to 0 if and only if x is equal to 0. And we have already seen that this implies P is invertible. Yeah, so we have actually learned two things in this, guys. One is how this representation happens when there is this change of coordinates, how the representation changes, right? It is through this matrix P. And moreover, we have also realized that suppose somebody gives me a basis, right, of a finite dimensional vector space. How do I get other bases? Well, just take an invertible matrix P. Yeah, look at those columns. From those columns, find out linear combinations. They will be your basis vectors. They will be another basis. Yeah. So this is the trick to create new bases. New bases. So I have V. V1 is given. V1 dot 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 up to Vn. Let P equal to P11, P12, and so on up to P1n. Pn1, Pn2, dot 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 up to Pnn. If n cross n be invertible, then W1 defined as P11 V1 dot 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 up to Pn1 Vn. W2 defined as, see, I'm just looking at the columns, huh? 1 2 V1 plus dot 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 up to P N2 Vn. I'm just looking at these columns. I'm picking each column and looking at the corresponding linear combination, finding out the vector for which this first column is the representation under the basis B1. Then looking at the second column, finding out the vector for which this is the representation, and so on. So that is how I'm getting these W1, W2, and so on up to Wn. This will give me P 1n V1 plus dot 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 up to Pnn Vn. Then W1 V2 defined as W1 dot 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 up to Wn is another basis. Prove that this is true. That goes to you as a homework. It's a very simple proof. It just uses the fact that P is invertible. So let P be invertible. Yeah, it just uses the fact that this is invertible. This is the idea of coordinates, yeah, which lets us treat vectors in a finite dimensional vector space, not just abstractly similar to columns of numbers, but literally as columns of numbers, as n tuples. That's the beauty of the coordinates. Before we finish, I give you some immediate attention and homework problems around this idea, around this notion, which if you solve, your ideas about these things will become much clearer. So first immediate attention problem is this one. We are doing change of coordinates. We are doing this coordinates idea over the coordinate space itself. Yeah, but now we are changing this, we are choosing a new basis. So we are having new representations. So that is what we are doing. In R4, we have these 4 vectors. I'm deliberately writing them as row vectors so that you also get used to row vectors. Yeah, there's nothing sacrosanct about column vectors. Find coordinates of each of the standard basis vectors, that is 1, 0, 0, 0, 1, 0, 0, 0, then 0, 0, 1, 0, then 0, 0, 0, 1. Those 4 basis vectors as linear combinations of this ordered basis v1 up to v4. Yeah. Then this is a problem which is very similar to the example that we have looked at during this lecture, involving e to the power exponential functions. Here I am saying that f1, f2, and f3 are 3 such e to the power exponential functions. You have to prove that they are linearly independent, as I've already told you to do so. And then part B says that suppose now I have 3 other vectors, 1 and then cos x and sin x. Yeah, so it's like new basis. See how the 2 bases are related through this P matrix. That's what this P matrix is, what you have to find out. And then there is this one homework problem which is similar, but now we are using polynomials instead of trigonometric functions. So try this one. Okay. Right. So I hope you enjoyed this part of the lecture. So if you have any doubts, as I have repeatedly told you, that if you have any doubts, please ask us questions. You have several different ways of asking questions. Yeah, you can post your questions as comments on the YouTube videos. You can post your questions as posts in the Google Classroom stream. You can also post questions on Moodle. You can directly ask questions to me by emails, right? So I hope you enjoyed this lecture number 5. It is a little different from the others. We have 4 modules this time. Okay, now we'll meet again for lecture number 6. Till then, it's a goodbye. Take care, stay safe, stay healthy. Bye-bye.